Hi everyone, this lesson is a continuation of the last about expected values of continuous probability functions. So here is a triangular function, a triangular distribution I should say. So the first task we need is we've been given the lower limit of 2, the upper limit of 12, and we've been told that the peak of the function occurs where x equals 10. Remember, 10 is not the height of this, 10 is an x value. So our job is to calculate the height. And again, the fundamental idea involved in this is that the area underneath that whole triangular distribution must equal 1. There is a lovely little rule that we developed last time that the height is 2 over b minus a. Now, if you don't remember that rule, just work out the height required so that a triangular area would have to equal 1. In our case, b minus a is 10, so 2 over 10 means the height of this distribution is 0.2. Now this one's a little bit more difficult because we need to get the equations of straight lines, the straight lines between these few points. So let me just draw the, oops, tried to draw that in red then. This point and this point and this point are going to be the defining values. So I'll write some coordinates. This one has coordinate 2, 0. This one is 10, 0.2, and this one is 12, 0.2. I'll end up with a piecewise function. I'm going to end up with a probability density function that has one formula up here where x is part of the domain 2 to 10, a different straight line formula where x is part of the domain 10 to 12, and I can fill in the last one. Everywhere else the value of the density function is 0. So I'm going to have to, now there are fancy little formulas that you can learn, but they're easy to get mixed up, so I've never bothered to learn them. If I've ever needed to work out the equation of a straight line, I just go off to the side and do it on the side here. So first we'll do the equation between the first one here between 2 and 10. So our equation of a straight line looks like y equals mx plus c. The rise is 0.2 divided by 0, divided by a run of 10 minus 2, which is 8. 0.2 divided by 8 is 0.025. Now I really need to calculate c, so I will substitute an appropriate x and y value. It's always easier to choose the one where y is 0. And x in this case was 2. It seems like 2 times that would be 0.05. C then is negative 0.05. That's my first equation. So I'll write it down over here. Gradient was 0.025 x plus, minus 0.05. Now the second one. Same thing really, y equals mx plus c. This time we're moving from, oh, there's a horrible little typo. The y coordinate of that point there is of course 0. Lucky I noticed that. So remember, it's alright to make mistakes as long as you notice them and fix them as you go. So this time we're going 0 subtract 0.2, and it's 12 take 10 would be a horizontal distance of 2 by x plus c. That's negative 0.1. Now I'll use an x value of 12 and a y value of 0. It looks to me like c is positive 1.2 in this case. Let's go and write that function over here. So my gradient was negative 0.1 and my intercept was positive 1.2. There's my probability density function. Now to find the mean value. The mean value of a density probability function is the integral between a and b of x by px dx. Because we're dealing with a piecewise function, we will have to perform two integrals, one from 2 to 10 and the next one from 10 to 12. And I have x multiplied by, now from memory it was 0.025x minus 0.05 dx. Memory is a bad thing. Yes. Plus the integral from 10 to 12 of x multiplied by, now that one was minus 0.1x plus 1.2. Oh, why did I put a bracket there so soon? Plus 1.2 dx. Now let's integrate straight away. This one between 2 and 10. I have to, of course, distribute the x by multiplying through. So I'm reading this as 0.025x squared. Integrating x squared becomes x cubed over 3. And this, of course, is 0.05x. Integral of x is x squared over 2. We do the same thing here. I imagine distributing the x through, and this is lower limit 10 this time, upper limit 12. So I have negative 0.1. This is really x squared. Integral of x squared is x cubed over 3. This is really 1.2x, so the integral is x squared over 2. Now that's a little bit of a tedious calculation, but when I performed that earlier, I found that this first one comes to 5.87, and the next bit comes to 2.13, and so I end up with a mean value for my triangular distribution of 8. Let's go back and look at where that lies. So there's the mean of 8, somewhat to the left of the highest value. Not really a surprise there, because this is a negatively skewed distribution. Most of the area under this distribution lies to the left of the peak value, so it's no surprise that the mean is also a little bit to the left of the peak value there. This time, though, it doesn't split the areas equally. If you did calculate out the areas, and you could easily do so, you could integrate from 2 to 8, you would find the area on this side is 0.45 and the area on that side is 0.55. So just because it's a mean doesn't mean it will split the distribution in half. The previous one did, but of course the previous one was a little bit special. It was a uniform distribution, so you'd expect symmetry to happen there. No reason to expect symmetry here, and as you can see, the areas are not symmetric, but the mean value always calculated by this formula. That's the main one to remember. If you use that each time, you'll be fine. Thanks for watching.